All right, welcome everybody. My name is Mats, and I am the engineering team lead for the Graph Data Science product at Neo4j. And today I will talk to you about fundamentals of using this product in its Series 2, which is the current major version that we are developing for. Pipelines is going to be a focus, but also a couple of other things. So let's get into it. Who am I? My name is Mats Rydberg. I live in Malmö, Sweden, which is also where we have our engineering headquarters. You see me on the lovely Scanian countryside in southern Sweden. I have been with Neo4j since 2015. I have a background in computer science where I hold a master's degree. Since joining Neo4j, I have been focused a lot around the Cypher language, both on the language design and implementation of the Neo4j database implementation of the language, which is, of course, Neo4j invented this language, but it's become a bit of an open standard. But ever since 2019, I have been focused more on graph algorithms. That was also incidentally the topic of my master's thesis. In order to support development of the Graph Data Science product. That's what I will be talking about today. And I have been the team lead of GDS on the engineering level since we picked it up. In this presentation, I will talk to you about some central areas of growth for the Graph Data Science product. And focusing on some new and some hot topics, also bringing in some oldies that I think deserve some attention in the new light of Series 2. So we'll do a bit of a background on what developments have been done during GDS, or rather since GDS was launched first in the beginning of 2020. Then we'll go into machine learning pipelines, talk a little bit about some central concepts that we discuss in the product and in the documentation. And I will go over to sort of dissect what these mean and also make sure that our terminology makes sense. I will talk a little bit about the GDS Python Client, which is a relatively new add-on product for the Graph Data Science product. And then we will do a revisit of graph projections, where we have done some new developments, and I want to give you a bit of information about how best to make use of the set of projections that we have, and what is a projection even. I'll talk about that. And towards the end, we will close with a demonstration, where I will show you some of these concepts in practice being used. So let's get into it. The background, a few highlights of GDS development. Well, it starts off with Series 1. 1.0 of GDS was launched in March of 2020, and it featured a graph catalog. This is still a core central concept. In the graph catalog, we have graphs projected from the database, the Neo4j database, using native projections or Cypher projections. And I won't go into the details of these. They have been with us ever since. It also came with a core set of algorithms focused in the community detection and the centrality categories. And there was an additional large set of inherited alpha algorithms from the predecessor project called Graph Algorithms, produced by Neo4j Labs. The difference between the two might be not so clear, but essentially those algorithms have been community implemented or not by us in core engineering. Fast forward a few months, we shipped GDS 1.3, incoming our node embeddings. This was a key development for empowering machine learning in particular. And with them came also the introduction of the model catalog, where we can store our machine learning models. 2 months later, the next year, 2 versions later, GDS 1.5 came. And now we actually don't just have node embeddings, but we've added machine learning models to the product. Node classification and link prediction in particular. And then 1.6 came with subgraph projections, which I will exemplify in the demonstration. I will also go through it towards the end of the presentation. And finally, at the end of 2021, we shipped 1.8, which was the last Series 1 version, and now entered the machine learning pipelines. So we constructed the pipeline concept in order to make it much simpler to do the machine learning and train the machine learning models to get the splits configured correctly and all the other parts that go into it. So, beginning of this year, GDS Series 2 launched in March, 2 years after the 1.0 launch. And now we only have pipelines for machine learning. We centralized on this core concept, and that's also the core concept that I will discuss in this presentation. We remove the ability to do anonymous graphs, making the graph catalog even more of a required component to think about. That's why I will go into the projections as well. New, a third kind of catalog, we have the pipeline catalog, and this one hosts pipelines. So pipelines are important for machine learning in GDS, and their home is in the pipeline catalog. Also, the GDS Python Client was launched together with the 2.0 series to make it easier to work with the library, especially if you have inclination for the Python ecosystem. In June of this year, we released GDS 2.1 with Apache Arrow imports to make it really fast to import from various data sources in the wild directly to the Neo4j Graph Catalog or the Neo4j database. We also added a third kind of machine learning pipeline, the one that I will focus on today. And then as late as last month, GDS 2.2 came along, and now we have graph sampling, which is I would say fifth way of doing projections in the library. We also have filtered pipelines. I will touch on this topic as well today in order to make the pipelines a little bit more powerful for richer graphs, such as knowledge graphs. But that's enough history for now. What's current and what's interesting? Machine learning pipelines are. So to introduce them, let's talk about a couple of concepts so that we can all really learn what we mean when we discuss certain terminology. So the machine learning pipelines, they are the GDS way to do machine learning. There's no other way to do it graph natively with this product. It enables using any of the GDS algorithms, be they centrality algorithms, community detection, or node embeddings, so that we can do feature engineering for our pipelines. There are 3 types, and they all fall in the category of supervised graph native learning. We have node classification. We have a set of nodes, and we might have 2, 3, 4, doesn't really matter, some kind of classes for the nodes, and we want the algorithm to learn which nodes belong to what class. We have node regression, where we have a property with a real value, and we want to make the model learn how to predict what that value is for unseen nodes. For example, it could be the average monthly traffic to a website. Why do I use this example? I'll show you later in the demo. We also have link prediction. This is the relationship-focused pipeline. So given a node pair, ought there to be a relationship between this node pair or not? That's what the link prediction pipeline is there to learn. The pipelines also offer support for auto-tuning. This is only for the model parameters. And what is the model? The model is also a training method. I will go over what that means in a bit. And the pipelines are really one of the major focus areas for development from our team. To produce new features, they will come wrapped somehow with new machine learning features will come wrapped somehow together with the pipelines in some sense. So they are currently exist in the beta and alpha tiers of maturity, and we're looking for your feedback before we fully nail down the API and call this the stable API that we will support for years to come. So please go out there, use them, and feed back what you think about it. So some of the concepts that we talk about in documentation and inside the product and in our presentations and so on refer to these pipelines. And it's good to have them in mind so that we are all talking about the same thing. So first come the concept of the training pipeline. This is the configurable object that lives in the pipeline catalog. It has to be explicitly created by the user, by you. Then it's in the catalog. It's a very lightweight object. It holds essentially just configuration. And you can configure it until you're done. And when you're done, you will call the train mode. And so you specify a pipeline and you'll train it, and then it will produce a trained model. The model then is an immutable object living in the model catalog. So you'll have your pipeline in your pipeline catalog, you'll configure it, and you can train multiple models with different configuration. And those models will end up in the model catalog, and then they don't change. They are produced through this train mode, and they can also be stored and loaded from disk with the persistence feature. This is a Graph Data Science Enterprise Edition feature. And they also wrap a so-called prediction pipeline. And the prediction pipeline is an immutable snapshot of the training pipeline at the time when train was called. So you're constructing your training pipeline, goes into the pipeline catalog. Eventually, you're happy with your configuration, you will train using this training pipeline. It produces a model, and the model then also contains what the state of the training pipeline detached from the training pipeline. Why is this useful? It's used when we do predictions. So when we have a model, we're not done. The model is a stepping stone for doing predictions. And when we can do predictions, then we get some value, if the predictions are good, of course. And so in order to repeat the node property steps of the pipeline, we will have to have a reference to what the training pipeline looked like when the model was trained. So what are node property steps? Node property steps are algorithms that produce node features. Could be embeddings, for example. It's a very typical use, but it could be other algorithms too. And the node features are, of course, used by the pipeline in order to help the model do predictions. Then we have the concept of context configuration. This is used used in filtered pipelines, also be called filter configuration. This is when we want to predict a particular pattern, but we, for example, we want to predict the link between users and, there, it will come soon, users that buy products. So we have users in our graphs, we have products in our graphs, users buy the products. And that's what we want to learn. We're doing a recommendation system. So if you're a user coming into our website, we want to give you the products that we think you're going to buy. And to do that, we might have to enrich the context for the node features so that the node features can take larger parts of the graph into account, such as where users live, what other users they might be related to, or on the product side, what other products were bought at the same time as this product, for example, and what other products have this user bought, and or completely different things like what categories does these products belong in. But we don't want to get all of that rich graph and make it available to the training algorithm, because if we do, the training algorithm could get confused and think, oh, well, maybe I'll recommend or predict the link between this user and this product category. That's not useful. So with the context configuration, we're able to separate these things apart. So let the training algorithm focus on what it's supposed to predict, and let the node feature, node property steps, learn more about the graph to produce better features. This is a new feature in 2.2, so you might not have heard of it, but now you do. Now you have. Then we have training methods. This is a thing that comes with many names in the machine learning ecosystem. Model architecture is another name. And to be concrete, what we're referring to with training methods is the inner model. It could be a logistic regression or random forest model, for example. We have a limited set of different training methods that we are adding on. Multi-layer perceptron is our latest training method. Okay, so what kind of pipelines are there? Well, I've already talked, or I rather mentioned, the node classification, link prediction, and node regression. And to save some time, I will not go into what node classification and link prediction are doing. If you're very interested in node classification, there was a presentation yesterday by my coworker Adam Schill-Karlberg, who focused on node classification. And later today, we have a presentation by Florentin Dörre, also my coworker, who will focus on link prediction. I will focus on node regression. So what is that? You see the alpha symbol that denotes the maturity tier of the node regression pipeline, which is the newest kind. So it starts out in alpha. What are we doing? We're training a numerical regression model using the node features, aka properties. We have linear regression and random forest training methods available to try out, see which one is the better one in our use case. The relationships of the graph are used by the node property steps, but not by the trainer itself. The trainer itself relies on more a traditional approach where we just look at the nodes and their features to determine what the value of what the value that we're supposed to predict with our regression model is supposed to be. We predict a real number for each node as a property when we do predictions. More things in the pipeline. Tuning, which is a new feature we shipped in 2.1. The auto-tuning algorithm is looking for good values. So you give a range for a hyperparameter, and it could be between 0 and 1, could be between 10 and 1,000. And the auto-tuning model will sample some values in this range and try them out. Then the models compete in the cross-validation phase. Eventually, a model will win. We'll have the best score according to the metric on the validation sets. And then that value is retained and sent back and also added to the winning model in the model catalog. You can configure the auto-tuning using a maximum trial budget to not let the auto-tuning try and run forever. Also, you can reduce the budget if it does run for too long. And currently, the auto-tuning support, which is relatively new, it supports training the numerical model parameters of all the training methods, but it does not extend to node property steps yet. So if you need this, please give us this feedback. And the context configuration that I talked about a little on the previous slide, this is a new feature in 2.2. Let the training focus on a particular pattern. Here is an example of a pattern, the one I explained with words a minute or two ago. For example, this is what it might look like for link prediction. And then you would say source node label user, target relationship type is buys, and the target node label is product in this example. And for node pipelines, you would give a set of target labels, for example. These are the ones you should look at when doing predictions. And while we restrict the training algorithm and the training method and the data that goes into it, we don't want to restrict our node property steps. So then they can focus on this larger context. That's why it's context configuration. And this helps to avoid predicting irrelevant combinations. All right. Fast forward to the next section, GDS Python Client. So what is this? Well, this is really a Python product, Python library. It's a wrapper for the Cypher Procedure API. Well, it's not really a wrapper. It produces Cypher code for you. And it introduces client-side helper objects for catalog management. So I've already mentioned we have the graph catalog, we have the model catalog, we have the pipeline catalog, 3 different catalogs. How do you use them? Well, they have their own procedures for listing and adding things in there and removing things from there. It can be a lot to type out in the Cypher code if you want to manage them. So to your help are these graph, pipeline, and model objects with the GDS Python client that we greatly simplify how to read from these catalogs and modify the objects in them. There are some specific features in the Python client for Aura DS. Aura DS is, of course, the cloud offered version of GDS and Neo4j. Specific features for arrow-powered imports to make that as smooth as possible. We call this graph construction. Results are typically returned as data frames when appropriate, or if it's just a single row, it's returned as just a series. This makes a conversion of the results a necessary step. You just get a data frame and you do your data science from there. There's the Python client has its own version. It's versioned separately from the server or the Graph Data Science library product. And the current version is 1.5. There's also its own manual. It hosts some new end-to-end example content on their GitHub repo, which is open source, of course, ready to run notebooks with data sets. There's tutorials in the manual. So it's very aimed at getting up and running quickly. And also to alleviate the need to learn Cypher and database driver management. So something we learned from our users is that they might come from a bit of a different background than our database users. So if you're a machine learning enthusiast, maybe you're a data scientist or a data engineer, and then learning how to operate the database might not be your first priority, or learning a new query language. You might want to stay in Python, and this client will help you do that. And the ambition really is that every user of GDS should be using the client. And we hope that there are no hindrances to doing so. And to support this, each new release of the client will support all the live GDS versions. So you don't have to worry. Just get the latest client and it will work with your server. You don't have to upgrade your server unless it's very old, of course. So you heard some code examples. So if you're familiar with the Cypher procedure API, you might recognize the parts highlighted in yellow here. That's exactly the procedure names. But now this is all Python code. So you don't have to say call in front of it, or you don't have to remember any other details of Cypher syntax. Just have to remember what the names are, which you can, of course, read from the manual. So graph construction, going from data frames directly to GDS. This is a new feature in the client version 1.3. You just do something like this, GDS alpha graph construct, to give it a name. You send in a couple of data frames, or just one, that contain your node data. You have similar data frame for relationships, and then you're done. And now your variable G here holds an in-memory graph, or rather it is a Python client graph object, which is a reference to the graph in the graph catalog on the server. It also comes with pre-canned data sets going from 0 to a graph immediately. So we just want to get in there and learn. This is a new feature in 1.4. It uses graph construct under the hood. Currently we have one, but we have plans of adding more in the next version. And the one we have is called Cora. It's a paper-to-paper citation graph. And so we can just run these lines, GDS graph load Cora. It will connect to your server instance and transfer the Cora graph into the catalog, give you the graph object back, and you can directly start running algorithms. Convenience objects, it's designed to be maximally convenient and Pythonic. So we have the graph pipelines and model objects, which help with managing the catalog objects, and we really recommend using these over the manually crafted Cypher queries. You get more portable notebooks and you have an increased Python footprint, and that's really what the client is for. So rather than doing something like this in browser or Cypher shell with Cypher, you can do the bottom half here. So you do just Python code and you get graph objects that you can interrogate for some of their statistics. Similarly for pipelines, instead of doing these long, for pipelines, they have particularly long names. You'll have to use the long name to begin with, but after that you can use the pipeline object, and I'll show you in the demo. See here outlined in red where the graph objects comes in. So then just quickly going over graph projections. The backbone graph projections, I hope, are well known. The native projections, of course, the map-based node and relationship projections, those are the fast, going from the NEF database to the graph catalog as fast as possible, concurrently scales really well, but they are a bit constricted in their expressivity. So we have the Cypher projections. And then you can just pass in one query, a node query, and one query for the relationships. They can kind of do whatever they want with the data in the database, as long as they return a shape that is consistent with one another and also has the correct names in the return fields. And then you get a graph from that. But there are more. There's a Cypher aggregation. This is a development of the Cypher projection, which we hope can overcome some of the shortcomings of the classic Cypher projections from version 1. We have subgraph projections that I mentioned. We have graph sampling. So Cypher aggregation is a new take, but it uses only a single query. It avoids using a procedure and integrates better with Cypher itself. So if you're used to Cypher, you might start by running a query or defining a query such as this. You have your classic match class. Here is the as a predicate. In this case, I'm using a subquery exists, where I'm looking only for users that have a relationship to a city of a particular name, pass in as a parameter. So it's a very customized set of users that have bought products, and those I want to add to my graph. So then I will the Cypher aggregation procedure and give it a name. I send in the user nodes, the product nodes, and I give them some configuration here for their properties. So I use the embedding property and the amount property for the relationship. And it's all Cypher. There's no procedure here. There's really nothing specific going on. So if you're used to Cypher, this will just work for you. Subgraph projection. This is a graph-to-graph projection using property filtering. So once you have a graph projected into the graph catalog, you can use the subgraph projection, give it a name, specify your base graph, and then a node predicate. In this case, I'm imagining that in the base graph, I have run a community detection algorithm. Now I have a community ID property on my nodes, and one of the communities has ID 42. And I only want a graph with those with that community. I'll use any relationship as well. That's what star means. And now I have that in the graph G community 42. So this is the key here to be successful with subgraph projections, that you can do these property value predicates. And the last of the projections is the graph sampling. It's another graph-to-graph projection, but this one uses stratified random sampling instead of predicates on the properties. So similarly, we just call the graph sample RWR. RWR is for random walks with the restarts. That's the algorithm. There might be more sampling algorithms in the future. We give it a name, we give it a base graph, and we give it some configuration. In this case, take 20% of the graph. That's what you're supposed to sample. And then we get a representative 20% sized graph from the base graph. And if you have particular sampling variants that you are in need of, please send us your requests. And now it's demo time. I have an issue. All right, issue resolved. So first, just a few things. You will install the Graph Data Science client using pip install Graph Data Science, and I'm using the latest version, 1.5. And then what we need to do is we need to connect to Neo4j. So I have a local Neo4j a desktop instance in the background, and I'm just connecting to it using this. This is what we need to do to get started. And I'm looking, oh, what version do I have? I have a bit of an older version, 2.2.1. Should actually be 2.2.4 or 2.2.3 or something. So what are we going to do in this demo? I'm going to show you a node regression pipeline using convenience objects. It's Python only, subgraph projection, a graph sample projection, and node regression pipeline. I don't have too much time, so I'll be going a bit fast. The input graph here is represents Wikipedia pages on particular topics, some animals, chameleons, squirrels, and crocodiles. And there's some links between these pages on Wikipedia. I think it was from 2017, 2018 timeframe. You can look at the source data using this link here. I will share the notebook afterwards. And the features are presence of certain informative nouns in the text of the page. That's the node features. Okay, so first off, we'll just project our graph. We get the loading bar. It goes really quick. It's not too large. But we're also using native projections, and native projections are just extremely fast. So what do we have? We have a new graph with this name. That's our input name, of course. We have 19,000 nodes and 860,000 relationships. Okay, so a good first analysis to do with our graph is to see how many components are there. We'll use the WCC algorithm to learn. And this is one of our fastest algorithms, and it runs, well, 15 milliseconds. We learned that there are 3 components. And we gave them all a component ID in the WCC component. And happen to know here that one of the components is going to be ID 0, and that's going to be the chameleon part of the graph. And so what I'll do is I'll do a subgraph projection to get a graph with only the chameleon animals in it. It's very common to only want graphs that are connected and not have these multi-component graphs because usually information doesn't flow where there are no relationships. So it's better to take the graphs one by one unless you have specific circumstances. So now we have a smaller graph. What was our result? Well, we ended up with 2,200 nodes and 72,000 relationships in our chameleon graph. So we can look a little bit closer at its statistics. Yes, we see those numbers again, and we have some degree distribution here. It seems our mean degree is about 31. Well, we have some super nodes here with 700 relationships. All right, and now we will construct the training pipeline. And we will do a node regression. We give it some kind of name here. And what we're getting back is a result that we're not going to focus on right now. So we'll just ignore that. And we'll get also back our pipeline object. And using the pipeline object, we are now can do all the configuration of the pipeline. So I'm just going to kick that off. What we're doing, so this is almost instantaneous because no computation is really being done. We're just saving all this configuration. We're going to use 20% test set in this graph, and we add a linear regression. We let the auto-tuner find a good learning rate for us, and I'm running out of time. So I'll just fast forward. Here we're training it. It takes a little bit of time. So what we're going to do is we're going to do a sample of the graph using only 30% of it. And notice that this is actually faster. I can't do that while I'm training here already. And then later on, what we're going to do is we're going to compare the training output of the graph that trained on the entire input graph and the one that trained on just the sample to see whether both are equally good, because this one takes, about half a minute, and then it's done. We get some kind of score. Is this good? We'll see. So we'll do this sample instead. This takes much shorter time. You see it progresses much faster. And then in the end, we're doing some predictions. And so we can determine whether we liked our sample down version instead. And that's me out of time. So I also want to give a shout out to my colleagues who are doing sessions on similar topics for graph data science. One was yesterday, one is later on today. And have some links here. This is mostly for sharing the slides later so you can see what's going on. And thank you for your attention.